Okay, so all right, let me go down here a little bit. Section 11.6, directional derivatives and the gradient vector. So, right now you can find the slopes of tangent lines going of a surface going in what direction? The partial derivative of, you have the partial derivative of x and the partial derivative of y. Okay. And those partial derivatives are like the partial derivative of x is the slope of a tangent line with respect to what direction? What direction? Well, hold on here. Maybe let me go. Well, okay, hold on. I think I need to go back here a little bit to refresh you on this. Okay, interpretations of partial derivatives. So remember this problem. Remember this problem back in section 11.3, where you were given a function, a paraboloid that opened f of xy equals 4 minus x squared minus 2y squared, and it was a paraboloid that opened downward, and you were finding partial derivatives with respect to x and y, and you had to interpret those numbers as slopes. So when x is 1 and y is 1, the partial derivative, and remember, you can, by the way, you can click on the screen twice if you want to blow up the, how many knew that? You can click on the screen twice to blow up the, enlarge the, what you're seeing on the screen. You just click on the screen twice. How many knew that? Or how try it and see. Does it work? Does it work for you? Okay, it works for Ryan, Christopher. Good. Okay, so you recall this problem. We computed the two partial derivatives at when x is 1 and y is 1. We computed the partial derivative with respect to x and the partial derivative with respect to y. And both those partial derivatives were negative. Okay, and then what we did was we looked at the picture of our surface in figure 2 here. The surface was z equals 4 minus x squared minus 2y squared. And there's the tangent line going through the point 1, 1, 1, because when x is 1 and y is 1, z equals 1. That tangent line is the slope negative or positive for that red tangent line passing through that point, that red point. Is the slope of the tangent line, so when we talk about a slope, you're looking at the rate of the change of z with respect to x. So looking at x in the positive direction, is the slope of the tangent line positive or negative? It's negative. That's right, Robin. And in fact, the value of it, that's right, Deodat, the value of that is -2. The slope is a -2. Okay. So, okay. And then if we go and look at the second figure, okay, here you have a tangent line to that point, and the tangent line is going in the direction of the y-axis. What's the slope of that tangent line? Is it positive or negative for figure 4? It's negative also. That's right. That's right. And its slope is -4. So far, these partial derivatives, when you evaluate them, they represent slopes of tangent lines with respect to the x-axis or the y-axis, or with respect to if we're talking about vectors, the partial derivative with respect to x is the slope of the tangent line looking in the direction of the I vector, and the partial derivative of the function with respect to y is, when we evaluate that, that's the slope of a tangent line with looking in the direction of the j vector. Okay, but that's great. That's great. But of course, there are many other directions we can consider than the direction of the x-axis or the y-axis. You know, the direction of the I vector or the j vector. There are many more directions that exist on a surface that we could look in, and those directions would also have slopes as well. So, like for instance, here in figure 3, this, now we're back to section 11.11.6. Here in figure 3, okay, here is a surface, and there's a point on the surface, and we're drawing a tangent line to that point on the surface. But the tangent line, what direction is that tangent line pointing in? What vector? That tangent line is parallel to what vector? The u vector. That's right. Good, Eric. Good, Robin. Well, the tangent line has a slope, right? That tangent line pointing in the direction of the u vector has a slope. It has a derivative. Well, how are we going to find it? How are we going to find it? Well, we have to develop some math to find it. So what we do is we recognize that in the xy plane, there's the vector u, and the vector u goes from a point P prime to a point Q prime. And if we consider going from P prime to Q prime, and those primes don't represent anything in terms of a derivative, they're just called that. If the vector u has, if the components of u are a and b, so they're saying here that the components of the vector u are a and b. Okay, so if the components of the vector u are a and b, then in the figure here, if we wanted to find the slope of the tangent line, we would bring the point Q prime closer to the point P prime. Well, that means then that I want to say this the right way, the PQ prime, the direction of it would be h times the vector u, which is HA, has components HA and HB. So formally, the directional derivative of a function at a point in the direction of a unit vector AD would be given by this definition, this formal definition here. You see there how you're letting both x and y vary? You're letting both x and y vary. If you think about the you know, the definitions of the partial derivatives, partial derivative of f with respect to x, you just let the x vary. Partial derivative of f with respect to y, of course, you just let the y vary. Okay, and so the partial derivative of f with respect to y, you let the y vary and you hold the x not constant. You hold the x constant. The partial derivative of f with respect to x, you let the x vary and you hold the y constant. Well, now, if you want a derivative in a different direction, you have to let x and y vary. And that's how we get to this definition of the directional derivative. The directional derivative of a function in the direction of a unit vector u, it's a unit vector, so it's standardized. That's the definition. And you see how you're letting x and y vary? How many think that's pretty cool? I mean, it's the derivative of a quotient, but you're letting x and y vary. How many think that's kind of fascinating? Robin likes it. Okay, and remember in Calculus 1, when you learned about the definition of a derivative, remember how you had to, before you learned the rules for the derivatives, you had to like use the quotient rule and use the definition to figure out values of your derivative. How many remember that in Calculus 1? And it was kind of a pain. And then but you learned some rules, and then you eventually used the rules to get derivatives more quickly. You didn't have to use the definition anymore. How many recall those times back in Calculus 1? Okay, Ryan does, and hopefully, if some of you, the rest of you do too. Is there another person who recalls that? Maybe it would be maybe nice to have another. Okay, the other Ryan does as well. So the thing is, you see, we could find derivatives using this definition. We could do it, but the problem is that it's difficult to do. Well, fortunately, mathematicians have come up with a way to compute a directional derivative without, well, an easier way. So here, this is a theorem in the book that says if you want to compute a directional derivative of a function in the direction of a unit vector u, where the components of u are a and b, the directional derivative is equal to the weighted average, basically, of or the linear combination of the two partial derivatives with respect to x and y, where the weights are a and b respectively. Okay, so like for instance, let me show you why this would maybe make sense. Let me go ahead and go to the whiteboard. Okay, and let me try to use my stylus here. Okay, so the directional derivative of a function, okay, with the directional derivative of a function in the direction of u is equal to a times the partial derivative of f with respect to x plus b times the partial derivative of f with respect to y. Draw that like that. And I'll note here, getting a little better with this, that the vector u is a unit vector and it has components a and b. So for instance, let's say you wanted the directional derivative of a function okay, in the direction of the I vector. Okay. Well, I, what are the components of I? 1 and 0. Good, Christopher. Okay, so the vector I, in order to see the direction in which we're looking in, we only need to use a 2-component vector. So the directional derivative then would just be equal to 1 times the partial derivative of f with respect to x plus 0 times the partial derivative of y. But what does that equal? That just equals the partial derivative of f with respect to x. So you see the when you're looking in the direction of the I vector, the directional derivative just becomes the partial derivative of f with respect to x, as we would expect it would be. On the other hand, what would the directional derivative equal if your unit vector is the j vector? That's right, Robin. Because, okay, for that vector, the j vector is equal to 1, 0, or 0, 1, sorry. 0, 1. So 0, 1, you get the partial derivative of f with respect to y. Are there any questions on that? Okay, let me know if you have any questions. One moment here. Sorry, just give me a moment. Okay, let me ask you this. What if you had a unit vector that were equal to this? Say, gosh, hold on. Say you had man, hold on. Say you had 1 over the square root of 100, and then you had the square root of 99 over the square root of 100. Okay, let's say this were your unit vector. And that is a unit vector. If you check that, you'll see that is a unit vector. And, you know, you're going to use here this definition for the directional derivative. Which of the partial derivatives for this vector here should have a greater influence when you compute the directional derivative based on that vector? Which should have a greater influence? The partial derivative of f with respect to x, or the partial derivative of f with respect to y? That's right, Ryan. The partial derivative of f with respect to y, and that would be you know, that would be this, because the b is so much larger than the a. For this, you know, the b is the square root of 99 over square root of 100 component. The a is 1 over the square root of 100. So does it kind of intuitively make sense? What I'm trying to do is give you an intuitive feel for this definition. They prove it in the book, but does this help you a little bit to kind of appreciate the definition? Does this little discussion help you appreciate it? Okay, thank you, Diadath. Thank you. Thank you. All right, very good, very good. All right, well, then let's go back to the book here. One moment here, I got to get the Mind tab back. Okay, here also, I'll just maybe, let me just mention this here. So the vector u has components a and b, but a and b also can, based on the picture here, can be represented as cosine of theta, sine of theta, right? Because what's the length of the unit vector? The length of the unit vector is equal to 1, right? So a and b could be expressed then as cosine theta, sine theta. And so we could represent this directional derivative, then we can represent it this way also, okay? Where a and b, the components are replaced with cosine of theta and sine of theta. Okay, that's just another way of expressing it. So let's look at an example here. Let's look at an example. Okay, here's example, hold on. Okay, here's example 2. Find the directional derivative if your function is equal to x cubed minus 3xy plus 4y squared. That's your function. And u is the unit vector given by the angle theta equals pi over 6. What's then the directional derivative of the function at the point 1, at the point 1, 2? Okay. So just out of curiosity, if theta equals pi over 6, what is the unit vector going to be? What are the components of the unit vector? If theta, so you know, draw a right triangle where theta is 30 degrees. I'm asking what x and y coordinates are for that angle. Let's see, Ryan, square root of 3 over 2.5, that is correct. That is correct. Okay, so let's go ahead and look at the directional derivative. Okay, here's the formula. Okay, and it's laid out here for you. Okay, are there any questions on, and we'll actually do a few examples for your notes too. But let's just look, we're looking here at example 2. Okay, are there any questions so far with what you're seeing? All right, well then let's continue a little more here. Okay, therefore, then the directional derivative evaluated at 1, 2 would equal, when you work it out, 13 minus 3 times the square root of 3 over 2. And you know that's what WebAssign wants. WebAssign, unless WebAssign tells you to approximate, round to the third decimal place or whatever, WebAssign is going to want an exact answer, and that's the right answer too. It's always the exact answer is always the best answer if you can get it, right? So let me ask you, so is this directional derivative positive or negative? If you take 13 minus 3 square root of 3 and divide it by 2, is that a positive number or a negative number? Is the slope positive or negative? That's right, it's positive. If you get the decimal, you'll see it's positive. So good Eric, how do we interpret this? How do we interpret this? Well, here's a little picture. Okay, here's a little picture. Okay. Just highlight the writing there for you. Let me see. Whoops. Okay, so the directional derivative represents the rate of change of z in the direction of u. This is the slope of the tangent line to the curve of the intersection of that surface in the vertical plane through 1, 2, 0 in the direction of u. So you see in figure 5, they have a surface, and they have the point 1, 2, 0 in the xy plane. And they from that point, they've now hold on one moment. Let me look at that figure a little bit better. Yeah, so from that point, let me just look at one thing here. Hold on, class. I looked at this earlier and I was comfortable. Now I'm okay, all right. So you see how that they draw a little line from the 1 to 0. They draw a little line here, a little line segment, and it's parallel to the x-axis. So the angle theta is measured, from like parallel to the x-axis. So 30, if you measure 30 degrees from that parallel line, you get that vector u. You get that vector u. That is square root of 3. The components are square root of 3 over 2.5. And so they draw a plane cutting through that vector u. And if you look at the intersection of where that plane intersects the surface, that the tangent line right where above 1, 2, like if you think about the surface of on the surface above 1, 2, 0, that point, and draw a tangent line, you can see that that tangent line would be positive, and that's what you're finding. That's what you're finding, and this is important. If your slopes of slopes of surfaces, we want to be able to compute slopes in any direction. Okay, you know, if like you're talking about a mountain and you want to compute the slope of the surface in a certain direction, you know, maybe that's where you're worried the avalanche is going to be coming from, you know, in a certain direction, you know, you want to be able to compute the slope in that direction. So, I mean, this is a really, really important kind of problem. I mean, you can imagine, right? So, are there any questions on this example? This example 2 that we just looked at? How many are like feeling at least somewhat comfortable with the directional derivative? Okay, Robin is, and Chris and Ryan. Okay, and Eric, wonderful, wonderful. I'm glad to hear it, very glad to hear it. Okay, all right, well, let's continue on a little more in the section. Let's continue on a little bit more here. So, all right, another important concept is something called the gradient vector. The gradient vector. Okay, so if we look at the definition of the directional derivative, the directional derivative can be written as a dot product. Isn't that amazing? The directional derivative can be expressed as a dot product of the vector of partial derivatives and the unit vector that you're interested in. And the vector of partial derivatives is known as the gradient vector. It's known as the gradient vector. So you can express the directional derivative if you hold on here. Okay, here's the gradient vector, and you can write the directional derivative then in this nice, with this compact formula. Okay. All right. And incidentally, we're looking at directional derivatives for functions of 2 variables. But this can be extended to functions of 3 variables. So if you go a little further in the book here, they talk about functions of 3 variables. Okay, and you know, there's the definition of a directional derivative for a function of 3 variables. And you have similar definitions for the gradient when you have a function of 3 variables. Okay, and you know, there's the gradient, and then you have a directional derivative as well, definition. Okay, so let me just see here. Yeah, so just want to make you aware of that. Let's go ahead and now get to a few examples for your notes. So let me go ahead here and bring up this. Hold on here. I think this is what I want. Yeah. Let's do an example or 2 here, okay, in our notes. All right, so let me give you a moment here to copy this down, okay? Okay, so let's look at this here. We want to find the directional derivative of a function. Okay, the directional derivative of a function at a point 2, -1 in the direction of 4, 4. So they're not giving you in this problem an actual vector. They're not telling you what the vector is or what the angle is, but they are telling you that we're at the point 2, -1, and we're looking in the direction of 4, 4. So we ought to be able to figure out the direction vector. And then, okay, we're asked, of course, is the surface increasing or decreasing in this direction? Okay, so I can move to the solution. Does everybody have the example copied okay? Okay, very good, Deodath. Very good, Ryan. Very good, Robin. Okay, all right, then let us proceed on here. So what I do is I use this definition for the directional derivative. Directional derivative is the dot product of the gradient vector with a unit vector. Now the unit vector u, we'll have to figure that out. But first of all, let me get the gradient vector. So I compute partial derivatives of f with respect to x and y, and I get the gradient vector. So, I mean, I think this up to here, I think it's pretty clear, but let me know if you have any questions. Okay, I'm going to let you copy up to here, and then we'll continue on. I don't want to get too far ahead of you. Okay. Okay, so now, if there are no questions, then let us proceed on then. So, okay, we're going to compute the gradient vector at 2 and -1, and it turns out it'll be -4i plus 8j. You'll notice that when I wrote out the gradient, I wrote it two ways. One is this notation here. Okay, that's the vector notation. You know, these symbols here are for a vector. And then the other is the ij notation. So either way is okay. Sometimes I like the ij notation, but I'll leave that up to you. Okay, we have our gradient vector. What do we need to find now? In order to compute the directional derivative, what vectors do we need to find? The unit vector. Good, Eric. In the proper direction. In the proper direction. So we're told that 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 we start off at the point, well, let me just see here. Let me just see, one moment. Maybe I can draw a little picture here. Okay. So here's X, here's Y. Let's say this here is 2, -1. Okay, we're like standing, I mean, we're at the point 2, -1. Okay, and of course on the surface, well, yeah, that's fine, that's fine. So, hold on, one moment. Let me just make a note here. One moment, class. So the surface value, f of x, y, when x equals 2 and y equals -1, I'm getting that to be actually 0. Yeah, so we're at the point, I mean, on the surface, we're at, hold on, I just want to make sure I'm saying it right. We're at 2, -1, 0. But the point is, we're looking in the direction of 4, 4. So here's 4, 4. Let's say 4, 4. I mean, we know where 4, 4 is. It's like right here, right? This is kind of sloppy. Let me make it look good here. Okay, there's 4, 4. And of course, this is my vector. So I could call that vector V. Okay, I could call that, sorry, vector V. How would I find that that vector? What do I do with the points? How do I find vector V? Good, that's right, Eric. P1 minus P0, so 4, 4 minus 2, -1. Okay, so, all right, we'll do that. And we get then 2, 5, the vector 2, 5. But keep in mind, we need a unit vector pointing in the direction of 2, 5. So we have to normalize the 2, 5. We have to standardize it so we get a unit vector. And the unit vector pointing in the direction of the vector 2, 5, well, if we standardize, sorry, if we want a vector parallel to the vector 2, 5, but it's a unit vector, that vector would be right here. 2 over root 29 times vector I plus 5 over root 29 times vector j. A lot of times students, they'll forget to get the unit vector. They'll find the vector in the direction, they'll get the right direction, but they have to then find the unit vector in that direction. And then you just compute the directional derivative. And this example that I'm doing is example 4 in the textbook. So, but I'm just I'm putting in some details for you. Let me know if you have any questions, and then I'll comment a little bit more here. I have a picture here. Obviously, I don't expect you to, you know, copy the picture down, but the picture is from, again, that's from figure 6, see example 4. Okay, let me give you a little more time to copy. Okay, so now we get the value of the directional derivative is square root of is 32 over the square root of 29. And keep in mind, what does that mean? You know, a derivative has an interpretation, right? It's a rate of change. Okay, rate of change of what? It's the rate of change of z, okay? The rate of change of your surface in the direction of the vector u at the point 2, -1. Okay. So for every 1 unit you move in the direction of the vector u, your surface will rise up 32 over square root of 29 units. That's what that means. The surface, therefore, is increasing. It's increasing at 2, -1 in the direction of the vector u. It's increasing. And of course, this is example, by the way, not I know how to spell. So what they do here in the little picture for this problem in figure 6, and this goes with example 4, is they drew a contour plot. They drew a contour plot of this function. And let me ask, as you move away from the origin, based on the contour plot, does the function seem to be getting steeper or getting shallower as you move away? You know, as you move away from the origin, you know, it's definitely getting steeper. Good, Robin. Good, Ryan. You can tell that because the contour, the level curves of the contour are getting closer together. And in fact, the surface is the surface increasing? Is it going upward, or is the surface going downward? What intuitively? It's going upward. And you know, the directional derivative, at least when you're looking in the direction of the, got to be a little careful. When you're looking in the direction of the vector v, in the first quadrant there, the surface appears to be rising. And the directional derivative confirms that. I mean, you could graph the surface in MATLAB and see. Yeah. So, are there any questions? Any questions on this? Okay, okay, well, then let's go ahead. Are we ready to look at another example? All right, let's look at another example then. Okay, let me give you a moment to copy this example down. Okay, so now here we have a function, x times e to the yth power. Okay, incidentally, now this function is, well, okay, let's just, in what direction, they're asking in what direction does this function have the maximum rate of change at the point 2, 0? So now they're not just looking for a rate of change. They want to know what the maximum rate of change is. In other words, in what direction is the surface increasing or decreasing? I got to be careful here. In what direction is the surface increasing the most? I got to be a little bit careful. Hold on. Let me just check one thing on that. Because rate of change, I want to be sure they're, one moment, class, one moment. Yeah, in this case, it's going to be where's the surface increasing, where is it increasing the fastest? Okay, in what direction? In what direction? If at 2, 0, okay, and really, yeah, okay, so that's fine, that's fine. So, well, let's take a look at how to solve this. So, first of all, I make note of the definition of a directional derivative. But then, oh my gosh, the directional derivative is a dot product. And this is, how many recall this definition of a dot product? The dot product is equal to the product of the lengths of the vectors times the cosine of the angle between the vectors. How many remember that definition back from chapter 9? Okay, yeah. I mean, you're used to A dot, Robin remembers it, A dot B. okay, equals the length of A times the length of B times the cosine of the angle in between. But that definition of the dot product, okay, that definition, that formulation, and let me make that dot a little better there. That definition of the dot product is true for all vectors A and B. And we have two vectors here. It's just one's the gradient vector and the other is this unit vector. So what I do is but the length of the unit vector here equals 1, right? The length equals 1. And so the directional derivative can be really expressed in this form right here. So where is the directional derivative maximized then? Well, it all relies on this angle here. It all relies on the cosine of theta. What value would be largest for the cosine of theta? What value would be largest? When theta equals 0. And so the directional derivative is maximized in the direction of the gradient vector. The directional derivative is maximized in the direction of the gradient vector, since the cosine of theta is maximized when theta is 0 degrees. I should just say 0, right? We should use radians, but you know what I mean. Let me give you a moment to catch up here. Let me know, please, if you have any questions, okay? Okay, so, well, the gradient, we evaluate the gradient vector, and then we evaluate the gradient at the point 2, 0, and we'll get the vector 1, 2. And so therefore, the surface increases fastest in the direction of 1, 2. And the maximum rate of change would just be the length of that gradient vector. That's what it would be. Absolutely fascinating. How many are thinking, who came up with this stuff? I mean, isn't it the most beautiful stuff you've ever, well, learned? I mean, look at what you're able to do here. And it's used a lot. It's used a lot. How many have seen gradients maybe in other classes? gradient vectors. Maybe not, but okay, Ryan's seen it in Physics 262. Okay. Okay. So this function, looking in the direction of the vector 1, 2, okay, is the surface rising, or is it going downward? Is the surface, so the function, remember, the function okay, the function was equal to, hold on here, it was equal to, right, x times e to the y power. Okay, so if you're at the point 2, 0, and you're looking in the direction of 1, 2, the x times e to the y power is the function. If you're at the point, you're at the point here 2, 0. All right, let's just say that's 2, 0. And you're looking in the direction of 1, 2, that vector, so you're looking in that direction. Would this surface here, well, the surface is rising, right? We know it's rising because you can even just tell by the equation, the function, that it's got to grow as x and y are positive. But also look here too, you have a positive rate here. So if we look at a picture here, this again comes from example 5, example 6, I should say, in your book. Here is a contour plot, okay, of your function. Again, that function is equal to, hold on, I just wrote it down. It's equal to x times e to the y power. And there's the point 2, 0, point P. And, looking at the scale, so 1, 2, the vector 1, 2, the gradient vector, I should say, is drawn here. Does it look like the surface is rising pretty fast in that direction? I mean, it does. It does. And in fact, in that direction, it's going the fastest. And what do you notice, incidentally, about, if you think about the level curves of the surface, okay, here's like I'll maybe put it in green here. Here's a level curve of the surface. What can you tell me about this angle here? This angle. what does that angle appear to be? What type? What? I mean, where the gradient vector crosses the level curves, it crosses it at right angles. That's right, Robin. 90 degrees. That is actually true. Incidentally, the gradient vector will cross the level curves. If you notice, every place, it's a right angle of 90 degrees. Every level curve. Okay, the point where the crossing occurs, where the gradient crosses the level curve, it crosses at 90 degrees, at a 90-degree angle. What I'm trying to say is, if you take the level curve, if you were to like take the level curve, the tangent vector of the level curve, and the gradient vector at every point of intersection, those two vectors will have a 90-degree angle between them, and that's no accident. Okay, are there any questions on that? All right, let us continue on. We have a little more to go here in section 11.6. So you have to excuse the background noise here. A little bit of okay. Hold on here. There was an example I wanted to show you here. Yeah, hold on. Where is it? Yeah, example 7. Example 7. Okay, suppose that the temperature at a point in space is given by that temperature function, where T is measured in degrees Celsius and X, Y, and Z in meters. In which direction does the temperature increase fastest at the point 1, 1, -2? Okay, what is the maximum rate of increase? And so I just wanted you to see this. I wanted you to see an applied problem. So they compute the gradient of the temperature function. Okay, they compute the gradient vector. And then they compute the gradient vector evaluated at 1, 1, -2. Okay. And so the temperature increases fastest in the direction of that gradient vector. Hold on here, I'm going to have to. Okay, and in the, hold on, one moment. Yeah, I'm recording. Thanks, Kurt. Thank you, Kurt. Okay, thanks everybody. All right. Thank you, Kurt. Thank you. Okay. Okay, the maximum rate of increase is the length of the gradient vector. So this is really kind of a repeat of what the problem we just did, but you compute the gradient vector, and the maximum rate of increase is going to be 5. Hold on here. The maximum rate of increase is going to be 5 divided by 8 times the square root of 41, which is approximately 4 degrees Celsius per minute. Or hold on. Hold on, one moment. I got 4 degrees Celsius per meter. Yeah. Okay. Are there any questions on that? I have one more thing to talk about here in this section. and then we'll, you know, I think I'll be able to let you work a little bit here. All right, if you're good with that, then let us proceed on. So there is a topic called tangent planes to level surfaces. So you've heard about level curves. If you take a surface, a function of x and y, and you set that function equal to a constant, that is going to create a level curve. Okay, and similarly, if you take a function of 3 variables and set it equal to a constant, you get a level surface. You get a level surface. So this is kind of like, oh man, if you think of like a snowball melting, okay, if you look at the snowball every hour, the snowball is like the shape of a circle, right? But I'm sorry, shape of a sphere, but it's melting and it's getting smaller and smaller and smaller. Every sphere is a level surface. Okay, every sphere is a level surface. And it turns out that based off of the equation here for a level surface, well, if x, y, and z could be regarded as functions of time, functions of t, okay, I want to say this the right way. Hold on here. So C, this curve C is any curve that lies on the surface and passes through a point on the surface. Okay, and you could use a vector function to trace out that curve. Okay, and similarly, well, the function of x, y, and z being set equal to a constant is a level surface. But x, y, and z are functions. You can be regarded as functions of t if because you're tracing out the points with that vector function r. I mean, this pictorially is a picture of what's going on, figure 9. Okay, so you're tracing out a curve on this surface. It's on the surface. Okay, you're tracing it out using the vector function r of t. And you want to find the equation of the tangent plane on the surface at the point P. Okay, well, remember, anytime you have a plane, an equation of a plane, you need to know a point on the plane, and you need to know a vector perpendicular to the plane. And it turns out the vector perpendicular to the plane, based on the figure 9, is going to be the gradient vector at the point. So why is this so? Why is this the case? Well, what they do is they say, okay, by the chain rule, since my big function f is a function of x, y, and z, and x, y, and z are functions of t, if I were to differentiate the formula, the equation of the level surface in the box with the 16 in it, formula 16, the chain rule would what you would get in formula 17 or equation 17. Just draw the flow chart and you'll see that's true. Well, that's fine then. But we can write formula 17 as a dot product of the gradient vector and r prime of t. Okay, we can express formula 17 here as the dot product of r prime and the gradient of the function. And so from there, we can then say, all right, the dot product of the gradient of a function at a point on the surface with the derivative of the vector r at the time such that you're at that point on the surface, that time t naught, t sub 0, that's going to equal 0. That's going to equal 0. And so from there, you're able to get the tangent plane to a level surface. Now, let me just see here. They talk then. I mean, this justifies in the picture now the fact that that gradient vector is perpendicular to r prime of t. And if you look in the equation above here, well, the gradient vector is the perpendicular vector to the tangent plane at point P on the surface, and x minus x 0, y minus y 0, z minus 0, z 0, they're just, part of the plane equation. So now you have a way to find the equation of a tangent plane to a surface at some point. And from there, we can go to example 8, which I think I'd like to mention here and have it in the recording. Example 8 says find equations of the tangent plane and a normal line to a point to the tangent plane. So they want us to find equations of the tangent plane and normal line to this point, -2, 1, -3 on that ellipsoid. Okay, we can do that. So we express the ellipsoid on the left side of the equation of the ellipsoid we express as f of x, y, and z, and then we compute the partial derivatives as you see here, and evaluate the partial derivatives at the point -2, 1, -3, and then we get the equation of the tangent plane. It's really quite amazing. It's really quite amazing what you can do. And of course, you can simplify that equation. And then if you want the equations of a normal line to the point. So like if we look at the picture here, hold on, if we look at the picture that goes with example 8, okay, here's the picture. You have the ellipsoid, and there's the tangent plane. Okay, there's the tangent plane, and then there's a normal vector, a normal line. We want the equation of we know the equation of the tangent plane. Now we want the equation of the normal line. Well, the normal line, remember, parametric equations of a line, you need a point on the line and you need a direction of the line. And we have that because the gradient vector gives the direction of that line, that red line there in figure 10, that's normal to the plane. And we know the point on the plane. So it's just a matter of then getting here are these symmetric equations of the normal line. Notice -1, 2, and -2/3 are the components of the gradient vector, and the line passes through the point -2, 1, -3. And so you have the equations, the symmetric equations of the normal line. And so, I mean, how many think this is really quite amazing what they're learning? I mean, truly amazing when you think about this. Okay, Christopher likes it. Robin, Eric, thank you. I know it's going to take some time to absorb. I know. Um, are there any questions? Are there any questions in general? Um, okay, let me stop the recording then.